Okay, here's an example of work energy principles applied to rigid bodies. Um, let's consider a slope with angle theta. Let's say theta is 30 degrees, but um, it doesn't matter. And we have a object, a disk, or some circular object. Of mass m, radius r, and moment of inertia ig about the center of mass g. Let's say the point of contact is p. Okay. Now we are told that object rolls without slip, and you're asked to determine, well, let's say the object starts at rest. Determine the velocity of g when g has descended, well, let's say g has traveled a distance s along the slope. Okay, so we've got initial g, and then it's gone down the slope by some distance s. This is initial, and this is final g, or something like that. Okay, and you can solve this by work energy principles. Let me first just quickly do it. So what is the work energy principle? It's Ke initial plus Pe initial plus any work done by other forces by which we mean not gravity or springs, equals Ke final plus Pe final. Okay, now let's go through these terms one at a time. What is Ke initial? The kinetic energy initial is 0 because you're starting at rest. And Pe initial, we can just set it equal to 0 by default, and let's say this is the datum, right? So that's the initial datum. This is y equals 0, and this would be yg would be equal to minus s. If this is theta, s times sine theta. Okay. So Ke final is not known. In fact, it's going to be half m vg square plus half I omega square, ig omega square. Okay. Now we are asked to find vg, but we do not know omega either. So that's that. But we can actually simplify this a little bit because it's rolling without slip. Without slip, we essentially have Vg equals well, depending on what your convention for omega is, it's going to be equal to minus r omega. So if you say this is the object, this is Vg, and this is omega, if this point is fixed, recall, this is what you get. So we've done this a few times in the previous two homework, and you basically get V equals r omega, and depending on the sign convention of omega, we either get plus r omega or minus r omega. In this case, it's going to be minus r omega because if this point is at rest, this is r, this is omega. Velocity of this point is going to be r times omega, but in this direction, but Vg is in this direction. That's why you get a negative sign there. Okay, so rolling without slip implies Vg equals minus r omega, which we can plug in here. So we can say Ke final equals half m Vg square plus half half Ig. Instead of omega square, we can say Vg by r square. And if you simplify it a little bit, you get half Vg square m plus Ig over r square. Okay, so that's Ke final. So what do we have so far? We have Ke initial, P initial, Ke final. What is P final? P final is mg and the value of y final. So that's going to be mg minus sine minus s sine theta. Okay, where that's this distance. Okay, this is g goes down by a distance s, so or along the slope, so vertically it would go by s sine theta, but because it's going down, it's minus s sine theta. Okay, so we got P final as well. So we can plug everything into this equation, except what is work done by other forces. What are the other forces on this problem? There's gravity, there's normal reaction, there is also friction because it's rolling without slip. Normal reaction does no work because the point of contact does not move in the direction of normal reaction, right? So this point is where normal reaction acts, and at that point the velocity of the disk is equal to 0. So whatever force acts at that point actually does no work because it's rolling without slip. So let me just write that down. What about work by normal reaction? Or friction? Okay, so recall work is integral F dotted with Vp dt, where P is point of application of the force. But for friction and normal reaction, let me just say both friction and normal reaction act at point P, and Vp of course equals 0, which is what we mean by no slip. This implies work equals 0, both due to friction and due to normal reaction. So okay, so that's it. And this is in fact why rolling without slip is so important, because rolling without slip means Vp equals 0, the frictional force does no work, so there is no dissipation of energy due to friction. This is why rolling without slip is such an important idea, and like we discussed, rolling without slip, namely the invention of a wheel, is such an important sort of milestone in history. Because it allows movement forward without friction doing any work. Because there is no slip, friction does no work. Okay, so let's plug everything into this equation. Plug everything into equation 1 using 1. We get K initial, which is 0, P initial, which is 0, work, which is 0, equals Ke final, which was half m plus Ig by r square Vg square, and then P final, which was minus mg s sine theta. And then we can simplify this, so we get Vg square equals 2mgs sine theta divided by m plus Ig by r square, or Vg equals square root of 2mgs sine theta divided by m plus Ig over r square. Okay, so that's the answer. Now, in other words, if you have an object like so, which is rolling without slip along a slope, the velocity it acquires is this quantity after traveling a distance s. We can, just to understand this a little bit better, we can consider a few cases. Consider, let me use green or something. Case 1, Ig equal to 0, which is basically, it's a particle. In other words, it's got no moment of inertia, it's a particle. So then Vg equals square root of 2mg s sine theta divided by m. M gets cancelled, and all you get is 2g s sine theta. So this is what you get if it's a particle. What if it was a disk? Uniform disk. Then you have Ig equals m r square by 2. So let's plug that into this expression. So we have Vg equals square root of 2mgs sine theta divided by m plus Ig by r square. Let's simplify this a little bit. M Ig by r square is going to be r square by 2. Okay, so that's going to give us, sorry, there's no, that's, the m doesn't get cancelled there. It's r square. R square and r square gets cancelled, and these m's get cancelled. So we have integral square root of 2mg, we can eliminate m as well, 2gs sine theta divided by 1 plus 1 by 2, which is 3 over 2. So you get square root of 4 over 3 gs sine theta. Okay, so that's Vg if you're a disk. So we can compare. So if it was a particle, it's square root of 2gs sine theta. If it was a disk, the velocity it acquires for traveling the same distance is 4 over 3. So clearly case 2 is acquires lower velocity than case 1. Why is that? And that's because what's happening here is this object starts at rest at some height and goes down by some distance or goes down by some height. That potential energy gets converted into kinetic energy. If you have just a particle, then that kinetic energy, particle with no friction, that's very important, particle with no friction, that potential energy gets converted completely to translational kinetic energy, and you get a relatively high velocity, like so. But if you have a disk, that potential energy gets converted partly to translational kinetic energy and partly to rotational kinetic energy. That's translational, partly to rotational kinetic energy. And because the potential energy is split between translational and rotational kinetic energy, you get overall a lower translational kinetic energy for a disk. Okay. Of course, if you had a particle, usually the case would be that there would be a lot of friction, which means that you would barely get any velocity. You wouldn't get a velocity like this. But in this case, it's kind of no friction case. Anyway, case 3, you could imagine, is a ring. Imagine a ring, then its Ig is actually mr square. And it's sort of even worse. So we can say Vg equals square root of 2mgs sine theta divided by m plus Ig by r square. And Ig by r square is just going to be m here. M plus m r square by r square. The r square gets cancelled, the m's get cancelled, and you've got square root of 2gs sine theta divided by 2, in fact. So, and that's going to be square root of gs sine theta. Okay, so Vg is square root of basically 1 times gs sine theta. That's for a ring. Okay, so you can compare a particle to a uniform disk to a ring, and it turns out a particle with no friction is the fastest because all the potential energy gets converted into kinetic energy. A uniform disk is next fast, at least with these 3 cases. And then the ring has the highest moment of inertia for a given radius, and because all the mass is concentrated at the outer rim, it's got the highest possible moment of inertia if all the mass is inside R, and has the lowest velocity. In this case, just 1 gs. This is 4 by 3 gs, and this is 2 gs sine theta with a square root. Okay, let's stop.